here's an example. It's the same example that is in the set of typed notes here. But let's suppose that we've got 5 parts that are inspected by 3 operators. M times a piece. So M equal to 10 inspections for each combination. And I want to lay out some hypothetical outcomes here. So here's part number 1, part number 2, part number 3, part number 4, and part number 5 as rows on a table. And as columns, we're going to have operator 1, operator 2, and operator, so I messed that up. Where first of all I'm going to list these, I'm going to list some p-hat values. So let's imagine that operator number 1 2 times in 10 calls the part non-conforming. Operator number 2 4 times in 10 calls the part non-conforming, and operator number 3 2 times in 10 calls the part non-conforming. If you average those 3 numbers, what you get is 0.2667, and that's the guy that I called p-hat bar. If you take that number times 1 minus that number, you get 0.1956. And if you take these 3 values and you put them into your calculator and hit the S squared button, what you will get is 0.0133. And in a sense, in rough terms, we're going to be more careful than this in a second with our calculation, but in rough terms, it is this that measures variability among the p-hat values, and so it's roughly that is related to reproducibility, and it is this that is related to overall. Okay, that's R and R. So roughly speaking, the S squared is related to variance among the p-hats. The 0.1956 is related to overall variation in the calls. Now, if I go ahead and fill this table in, let's suppose for sake of argument 6 times in 10 part 2 is called non-conforming by operator 1, 6 times in 10 by operator 2, 7 times in 10 by operator 3. Those average to 0.6333, and if I take 0.633 times 1 minus that, I get 0.2322, and if I compute the sample variance of 0.6, 0.7, sorry, 0.6, 0.6, and 0.7, I'll get 0.033. Okay, so part number 3, then we're going to suppose that operator number 1 makes 10 out of 10 calls non-conforming, operator number 2 makes 8 out of 10 calls non-conforming, operator number 3 makes 7 out of 10 calls non-conforming. If you average 1, 0.8, and 0.7, you get 0.8333. If you multiply that by 1 minus 0.8333, you get 0.1389. And if you take a sample variance of 1, 0.8, and 0.7, you get 0.0233. For sake of argument, we'll suppose that part number 4, each of the operators made a single non-conforming call in 10 trials. That gives an average of 0.1, and 0.1 times 0.9 is 0.09, and the sample variance of 3 numbers that are the same is 0, so that guy turns out to be 0. And finally, we'll suppose that on part number 5, operator 1 made 1 in 10 calls non-conforming, the other 2 made 3 in 10 calls non-conforming. If you average those 3 numbers, you get 0.2333. If you take 0.2333 and multiply by 1 minus that, you get 0.1789, and the sample variance of those 3 numbers is 0.0133. Those are raw materials for making R&R calculations. We're going to make those R&R calculations one part at a time and then average across parts. So beginning with part number 1, let's think about what I would have for the estimate for sigma squared reproducibility. Sigma squared reproducibility, what I need to do is take m, which is 10, times the s squared for the p-hats for part number 1, and that is 0.0133, and subtract the p-hat bar times the 1 minus p-hat bar. So I'm going to subtract this 0.1956 from that, take that whole thing and divide by 9, which is 10 minus 1. That thing turns out to be negative, and so when I take the max of 0 and this, I'm just going to get 0. So from that first part, my estimate of reproducibility variance is 0, and that means that my estimate of repeatability variance is going to be the difference between this 0.1956 value, that is the average p-hat times 1 minus the average p-hat, and 0, so it's just 0.1956, and the sum of those two things then is, of course, sigma hat R and R, that is 0.1956. Now, what does this say? This says that, yes, there are differences between the p-hat values, but the intrinsic binomial variation, okay, this thing is a measure of sort of average binomial variance that is so large that sure, there are differences between the p-hats, but if we had to make a best guess at how much variance there really is between the p's, we would estimate that variance, how much those things vary, we would estimate that to be 0. If you fill out the whole table of these estimates for part number 1, part number 2, part number 3, 4, and 5, your sigma hats for R and R, sigma squared hats for R and R, these average p hats times 1 minus average p hats, those values will look like 0.1956, 0.2322, 0.1389, 0.0900, and 0.1789, and those average to 0.1671. If you compute the estimates of the reproducibility variance, the first two are 0, the third is 0.0105, those two guys are 0, and therefore these average to 0.0021. And if you make estimates of the repeatability variance here, this is 0.1956, this is 0.2322, this guy is 0.1284, this is 0.0900, and this is 0.1789, which not too surprisingly averages to 0.1650. And the point is that this is a very small fraction of that, this and that, total to the sigma squared hat for R and R. For example, if I take 0.0021 and I divide it by 0.1671, that is about 1.3%, and it appears that reproducibility is a small contributor to overall variation in these ones and zeros.